Now let's see the next topic, that is graph isomorphism. What is the definition of graph isomorphism? This isomorphism, remember this word in any field. Okay, whether you study physics, chemistry, mathematics, whatever you study, that is your choice. Whatever you study, this isomorphism, this word will always mean that basically they are almost same, means same structure. Isomorphism means same structure. Okay, whatever you study, whatever field you study, this isomorphism means same structure. This iso means same, this iso means same, and this morphism means form. This morphism means form. Iso means same and morphism means form. So basically same form. So I can say, what is the definition of graph isomorphism? That is the same graphs. If you watch in the abstract view, the graphs are same. The graphs are same in abstract view. Abstract view means, okay, basically if you remove the labels and all. For example, if I give you these two graphs, like for example A, B, C, this graph and this graph, 1, 2, 3, are they same? Can you notice? These graphs are actually same. Why these are same? Because they are abstract view. If you notice their abstract view, they are actually same. If you notice their abstract view, they are actually same. So these two graphs are actually same. If you notice their abstract view. Now similarly, okay, A, B, C, D, this graph and A, C, D, B. Tell me, are these two graphs isomorphic? Like for example, can I say they are basically same? They are basically same. I told you that drawing does not matter. Drawing does not matter. In a graph, drawing does not matter. Basically, they are same, because ultimately, what is this? Ultimately, what is this? If you take this B, if you pull this B, okay, here, what you do? You pull this B here. You just pull it. Okay. So if you pull this B, then what will happen? It's like this. See, it's like this. You take this B, okay, you pick this B, and what you do? You pull this on this side. Then finally, ultimately, you will get this graph. So yes, these two graphs are also isomorphic. So they have the same form. So same graph in abstract view, or I can say they have the same form. Very simple. Is this clear? It does not matter. Label does not matter. See, this label and all these things does not matter. Basically, these graphs have the same form. Yes or no? Is it clear? This is just twisted. I can say this is just a twisted version of this graph. I can say this is just a twisted version of this graph. This is your G, this is twisted G. So basically both are same. Now let's see some example. For example, this is a meme you can notice. So these two graphs, this is a popular meme nowadays. Maybe you have seen this, right? Okay. So find the difference between these two graphs. Corporate needs you to find the difference between these two pictures. They are the same pictures, because ultimately they have the same thing. If you notice, the design does not matter. They are basically the same. For example, these are the isomorphic graph. This is the G and this is the twisted G. This graph is your G and this graph is your twisted G. Yes or no? So this is the simple, this is your, basically I can say this is your isomorphism. If you say this is G, then this will be twisted G. Okay. So that is the idea. Next. So basically this is the meme for graph isomorphism. Okay. Next. Okay. So if you want to share it someday, then maybe, okay, I can put this Go classes here just for credit, just for publicity. Okay. So maybe you can share it. Okay. Now let's see. So this is your graph isomorphism. This is your graph isomorphism, right? Okay. So basically this is your graph isomorphism. This is called marketing. Okay. Next. So is this graph isomorphism? Is this graph isomorphism? Please say no. Please say no. Okay. So this is not graph isomorphism. But anyway. Now let's move on. So let's see. So what is a graph isomorphism? These two graphs, if you notice, then these two are basically, they are basically same. So what does not matter? What does not matter? The labeling does not matter. See, the labeling does not matter. The label does not matter. Correct? Are these two graphs same? Can I say these two graphs are basically same? No, 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 no. Because in this graph you have a vertex of degree 3. In this graph you don't have a vertex of degree 3. So they are basically different. Actually, they are isomorphic, but these are not isomorphic. These two graphs are not isomorphic. They are very different from each other. This is a path graph. This is not a path graph. Yes or no? This is your P4. This is not a P4. Correct? So this is the idea. So these are not isomorphic. So in a graph isomorphism, what does not matter? What does not matter? In graph isomorphism, what that means basically? Graph isomorphism, what is the idea behind graph isomorphism? Idea is very simple. Idea is like this, that labeling does not matter, first of all. Okay, so this labeling doesn't matter. This labeling doesn't matter. So what you label, that doesn't matter. And also what doesn't matter? So this labeling doesn't matter in graph isomorphism. Also the design, the drawing does not matter. How you draw, that does not matter. How you draw, that does not matter. Okay. So whether you do twist, okay, twist does not matter. So these things basically, these things do not matter in graph isomorphism, all these things. So shape, yes. So the shape does not matter. The shape does not matter. All these things, they do not matter. Okay. Ultimately, what matters? There are many things that matter. Basically, for example, the degree sequence should be same. There are many things that should be same. Okay. So now let's see the formal definition. See, for example, if I give you this graph AB, and if I give you this graph AB, are they isomorphic? These two graphs G1, G2, are they isomorphic? These two graphs are not isomorphic, because you can notice that in this graph, this is a path graph, this is an empty graph. So these are very different graph. Yes or no? So these are not isomorphic. These two graphs are not isomorphic. What about these graph? A, B, C, D. Okay, what about this graph and this graph? Are these two graphs isomorphic? Are these two graphs isomorphic? No. This is your K4. This is not K4. This is not a complete graph on 4 vertices. This is complete graph on 4 vertices. But tell me, are they isomorphic? They look very different. Yes or no? They look very different. But are they isomorphic? Are these two graphs isomorphic? They look very different. But are these two graphs isomorphic? Yes, they are isomorphic. Because this is also K4. This is also K4. This is also complete graph on 4 vertices. This is also complete graph on 4 vertices. In this also, every vertex is adjacent to every other vertex. In this also, every vertex is adjacent to every other vertex. So both are basically K4. Ultimately, the design does not matter. The drawing does not matter. The design does not matter. Okay, these things do not matter. But ultimately, they are K4. This is also K4. This is also K4. These two are same. Now let's see one more example. For example, I can say this Q, this graph, this is your, which graph is this? Can anyone tell me which graph is this? This graph is your Q3. This is your Q3 graph. Okay. Now, are these two graphs isomorphic? These two graphs, are they isomorphic? These two graphs. Yes, they are isomorphic. They look very different. They look very different. This is a 3D picture. This is a 3D picture. This is a 3D drawing, I can say. This is a 3D drawing. And this is a 2D drawing. This is a 2D drawing. And that was a 3D drawing. But anyway, they are basically same. Everything is same. This is also Q3. So this Q3 you can draw like this, or this Q3 you can draw like this. Basically, they are basically Q3. Now, let's see. Now let's see the formal definition. What is the formal definition? What is the formal definition? Because so far we have seen informal definition, but what is the formal definition? First, you understand the idea behind the formal definition. Okay, so let's understand the idea. Have you seen a movie? For example, many times Bollywood movies are basically copy of this South movies. Okay, so for example, if you have a in South, there is a movie in South. This is actually my favorite movie, so I'm just taking its example. There is a South movie Drishyam of Mohanlal. Drishyam. This is a like brilliant movie. You can watch it. This is very nice movie. Okay, Drishyam Part 2. So now, anyway, so there is a movie Drishyam, and there is a sequel of it in the Bollywood that is also Drishyam. Like I don't know what is the like name in the South language. I don't know the name, whether the name is Drishyam or not. I don't know. But what I'm saying that there is a South movie Drishyam and there is a Bollywood movie Drishyam. Okay. Now, in this movie, actually, can I say they are isomorphic? Just think about it. Can I say they are similar? These two movies, how can I say they are similar? These two movies are similar. How can you say these are similar? These are similar because just think about it. Just think about it. This character, can I say this character has a corresponding character here? Tell me, can I say this character has a corresponding character here? Who is the corresponding character? Can I say Tabu is the corresponding character? Can I say Tabu? No, Tabu is not the corresponding character. The corresponding character is Ajay Devgan. Okay. So next, so this, okay, in the South India, you have this actor in this movie. This vertex, basically, it's like this. Remember, this vertex has a corresponding vertex here. So remember, this is your vertex. This is a vertex, and this has a corresponding vertex here. Similarly, this heroine, what is the actress name? I don't know. I forgot. Can anyone tell me what is the actress name? Who is the wife of Mohanlal? Who is the wife of Mohanlal in that movie? Shreya Sarani is in the Bollywood. Who is the wife of Mohanlal? Okay. Anyway, forget about it. So she is basically Mohanlal's wife. Okay. So she is basically wife. Let me call it. Okay. So she has a corresponding character here. She also has a corresponding character here. So she is a vertex, and this vertex has a corresponding vertex here, and that corresponding vertex is Shreya. Okay. Next, so there is a police. There is a female police inspector. There is a female. There is a female police lead, and she has a corresponding. This vertex. Remember, this is a vertex. In this graph, this is your graph. Remember, this is your graph. Okay, this is your graph. Now, what I'm saying that in this graph, this vertex has a corresponding vertex here, and that vertex is Tabu. Okay, so like this, and so on. Okay, and so on. So basically, every vertex has a corresponding vertex here. Correct? Yes or no? Very simple. So this is the idea that these two movies are isomorphic because this graph and this graph are isomorphic because there is a correspondence. There is a correspondence between the vertices of this graph and vertices of this graph. There is a correspondence. There is a bijection. There is a one-to-one bijection. Yes or no? There is a one-to-one correspondence between these vertices and these vertices. There is at least one bijection, such that what should happen? Is this enough? Just think about it. Is this enough? Is this enough? This is not enough. What is enough? See, if they have dialogue, if they have some dialogue, then they should also have a dialogue, similar dialogue. Yes or no? If they have dialogue, then they should also have a dialogue. Agree or not? For example, that popular dialogue, that 2nd October dialogue. Do you remember the 2nd October? Where was Ajay Devgan and his family on 2nd October? So that story, that dialogue is here also, here also. If some dialogue is here, if you have some dialogue here, then that dialogue, that same dialogue should be here also. And if there is no dialogue, just think about it. If there is no dialogue between these two, if there is no dialogue between these two, then there should be no dialogue between these two. Yes or no? Because this corresponds to this and this corresponds to this. So if they do not have any dialogue in this movie, then they should not have any dialogue in this movie. I hope this example is clear. This is just the idea, like, okay, just to explain the idea of isomorphism. And this is your isomorphism. This is the definition of isomorphism. So when can you say that two graphs are isomorphic? You have a graph G, V, comma, E, and you have a graph H, which is V2, comma, E2, which is V2, comma, E2. This is your graph V1, comma, E1, and this is graph V2, comma, E2. Then what is the definition of, see, G is isomorphic to H if and only if there exists, please notice this, please understand the definition, because I tell many times this point, I tell many times that anyone who understands the definition, you have already cracked the GATE exam. If you understand the definition, I give you some definition, you think about that definition. If you understand that definition carefully, then you have cracked the GATE exam. I guarantee you that. Because many people, they do not even try to understand the definition in front of them. So just understand the definition, you will understand everything. So G is isomorphic to H if and only if there exists, this is important, there exists a bijection. There exists a bijection between V1, comma, V2. Okay, means these vertices and these vertices. This is a movie, this is a movie. There should exist a bijection between the characters, yes or no? Agree or not? So what I am saying that in this movie, if you notice in this movie analogy, what is happening in this movie analogy? This is happening that this Drishyam South is what? In this analogy, tell me, this Drishyam South is what? This is the graph, yes or no? And this Drishyam South, Drishyam Bollywood, what is that? That is a graph. So in this analogy, basically, in this analogy, this is your graph G. This is basically your graph G, V1, comma, E1. And this is basically your graph. This is basically your graph H. This is your graph H, V2, comma, E2. Okay. So you have two graphs, V1, comma, E1. Correct. So in this analogy, the movie is basically the graph. Okay. And the characters are what? Tell me the characters are what? The characters are what? The characters here are the V1 and the characters here are the V2. Here the characters are V1. The vertices are the characters. These are the characters. Okay. And dialogue between two people. And dialogue, if you have some dialogue between A, comma, B, dialogue between A, comma, B, that is basically age between A, comma, B. That is basically age between A, comma, B. Yes or no? So the dialogue between two people, that is basically the age between two people. Okay. And if there is no dialogue between two people, then there is no age between two people. So this is the movie analogy. In this movie analogy, you can understand that when can I say that these two movies are isomorphic? I can say two movies are isomorphic. Tell me, when will you say two movies isomorphic? Isomorphic. If and only if there must be a bijection between the characters. Correct? There must be bijection between the characters. You must have a bijection between the characters. So there must be a bijection between there must exist a bijection between the characters. You must have a bijection between the characters. This bijection should preserve, remember, this bijection should preserve dialogues. Should preserve dialogues. This should preserve dialogue. What it means? This should preserve dialogue. What this means? This means that if there is a dialogue between A, comma, B here, then there should be a dialogue between FA, comma, FB here. And if there is no dialogue between C, comma, D here, if there is no dialogue between C, comma, D here, then there should be no dialogue between FC, comma, FD here. Yes or no? Is it clear to everyone? So the two movies are isomorphic. When can I say two movies are isomorphic? When their characters, you can put their characters in one-to-one correspondence. These are the characters, Mohanlal wife, this female police officer. Okay, and these are the characters here. So when you can put the characters in a one-to-one correspondence, such that, this is important, such that the dialogues must be preserved. Means If these two people have a dialogue, then their images also should have a dialogue. If these two people have a dialogue, their corresponding character here also must have a dialogue. If these two people don't have a dialogue, then their corresponding character must also not have a dialogue. This is the definition of isomorphism. So isomorphism definition says that two graphs are isomorphic if and only if there exists a bijection between V1 V2 which preserves edges. Which preserves edges. What it means? It means that A comma B, okay, it means that A comma B, they belong to V1. Okay, so A comma B belong to E1 if and only if they belong to E1, if and only if their corresponding, their images, their corresponding characters, they belong to E2. Yes or no? So they should preserve edges. Means A comma B, they have edge if and only if their images also have edge. And if they don't have edge, then their images also don't have edge. So they should preserve edges. The definition of isomorphism, is it clear to everyone? Please tell me. Is the definition clear? Because in the GATE exam, they can ask you the definition also. There is a question, there is a very, very, very nice question in the NET exam. In that question, they are asking definition of graph isomorphism. Okay, and what they will do in that definition, what variation they will do? This type of variation they will do in that definition. This type of variation they will do. There is edge between A comma B if and only if there is edge between their corresponding characters in the other graph. This is the idea. Okay, so let's understand this by example. So why these two graphs? For example, A, B, C. This graph, let's call it G. Okay, and let me give you another graph, 1, 2, 3. So why these two graphs are isomorphic? What can you say? What is the reason they are isomorphic? Tell me. Prove they are isomorphic. Prove they are isomorphic. So how will you prove they are isomorphic? To prove that they are isomorphic, if you want to prove that they are isomorphic, to prove what you have to do, if you want to prove they are isomorphic, what you have to do? You have to give one-to-one correspondence. You have to give one-to-one correspondence. You have to give a bijection between these vertices. You have to give a bijection between these vertices. At least one bijection you have to give which preserves the edges. Which will preserve the edges. So can anyone give me a bijection which will preserve the edges? Tell me, will this bijection work? Let me give you a bijection. Will this bijection work? This bijection, will it work? This bijection will not work. This bijection will not work. Why this bijection will not work? Why this bijection will not work? See, this is a bijection that is fine. Bijection is fine. Remember, bijection is fine. You must have a bijection between V1, V2, which preserves the edges. Which preserves the edges. This is very important. Which preserves the edges. What it means? What it means? It means that if they have dialogue, then they should also have a dialogue. Yes or no? See, this bijection will not work. Do they have a dialogue? Tell me. These two characters, do they have a dialogue in this graph? In this graph G, these are the graph G and these are the people of H. Do they have dialogue between these two? A comma B. Yes, they have dialogue, right? So yes, they have dialogue. Now they also should have a dialogue. Do they have a dialogue? Do they have a dialogue? Means they have an age. These two people have age, but their images don't have age. Their images don't have age. Yes or no? So ages are not preserved. See, AB has age. Now you can notice that one thing you notice, AB belongs to E1. AB belongs to E of G. But F of A, comma F of B does not belong to E of H. So you can notice A, comma B, they have dialogue between them, but their corresponding characters don't have dialogue. So this bijection will definitely not work. So can I say they are not isomorphic? This bijection will not work. So can I say they are not isomorphic? No, because remember there exists a bijection. This is the important point. There exists a bijection. There exists a bijection. If this bijection is not working, try something else. If this bijection is not working, try something else. Okay, so let me try. Let me try. Let's see, will this bijection work? So let me do this bijection. Will this bijection work? Please tell me. Will it work? This bijection will also not work. This bijection will also not work because 2, 3, they have dialogue. 2, 3, they have dialogue. A, B also have dialogue. That is fine. Very good. There is no problem. But why this bijection will not work? Why? What is the reason this bijection will not work? This bijection will not work because they have dialogue, right? See, if you notice, these two people, they don't have dialogue. B, C, they don't have age. B, C, they don't have age. They don't have age. But 3, 1, they have age. So this bijection will also not work because this bijection is not preserving ages. You can notice B, C does not belong to E of G. B, C does not belong to E of G, but F of B, F of C, that belongs to E of H. So I can say yes or no. So this bijection will also not preserve the edges. The edges are not preserved. So what to do? So can I say this is not isomorphic? How many bijections we have to check? Can anyone tell me? Please tell me. How many bijections are there? We have to check. How many bijections? Total 6 bijections are possible. Total 6 bijections are actually possible. If you notice, there are total 6 bijections possible. 3 factorial. Number of bijection possible is 3 factorial. So total 6 bijections we have to check. One of them should work. Remember, total 3 factorial bijections we have, but we only care about one bijection. We don't care about these bijections. We only care about one bijection. So which bijection will work? You can check this bijection will work. ABC 3, 1, 2. You can check this bijection will work. This bijection will work. This bijection will also work. Remember, this bijection will also work. So that is the reason there exists. This will also work. So 4 bijections will not work, but 2 bijections will work. Yes or no? Is it clear to everyone? See, these 2 bijections are not working, but these 2 bijections are working. And we only want one bijection. This bijection is working. Why? See, notice that A, B, they have age. 3, 1, they also have age. A, C, they have age. 3, 2 also have age. B, C don't have age. 1, 2 don't have age. So everything is working. Yes or no? See here. Check it here. A, B have age. 3, 2 have age. Next, B, C don't have age. 2, 1 don't have age. So everything is working. So ages are preserved. So this bijection will also work. This bijection will also work. And we only want one bijection. There exists a bijection which preserve the ages. So you can notice this bijection will preserve the ages and this bijection will also preserve the ages. So finally, I can say they are isomorphic. Is this clear to everyone? Please tell me, is this clear? Now let's see another question. These two graphs A, B, C and this graph A, B, C, this graph, are they isomorphic? Prove they are not isomorphic. Prove they are not isomorphic. How will you prove they are not isomorphic? How will you prove they are not isomorphic? What you have to do if you want to prove they are not isomorphic? What you have to do? What you have to do to prove that they are not isomorphic? No bijection will work. Now you can notice no bijection will work. Whatever bijection you create, that will not work. So basically no bijection. Total 3, see, there are total 3 factorial bijections are there. We have total 3 factorial bijections. This is your G, this is your H. 3 factorial bijections between vertices of G, vertices of H. but none of them will preserve edges. None of them will preserve dialogues, will preserve dialogues, or will preserve edges. So none of them will preserve edges. Whatever you do, very simple. There is a bijection. Don't say there is no bijection. There are 3 factorial bijection we have. So bijections we have between Vg comma Vh. We have total these many bijections we have. We have bijections, but they don't preserve edges. Whatever bijection you create, that will not preserve edges. See, they will not preserve edges. For example, if you take this bijection, let's assume that you take this bijection ABC, ABC. Now let's assume you take this bijection. Will it preserve edges? Let's assume you take this bijection. So tell me, for example, let me give you this bijection. Will it preserve edges? This bijection is not preserving edges because you can notice there is no edge. There is no edge between B comma C in G. In G, this is your G. In G, there is no edge between B comma C, but there is edge between C comma A. Between C comma A, there is edge in H. In H you have. So whatever bijection you create, that will not so these many bijections we have, but none of them will preserve edges. Tell me how many bijections you have from set. This is my question. Okay, number of bijections. Number of bijections. Number of bijections. How many bijections you have? Tell me. For example, if you have a if you have set A whose cardinality is 3, and there is a set B whose cardinality is 2. How many bijections you have? So number of bijections. Tell me. Number of bijections from A to B. Okay, from A to B, number of bijections between A comma B. How many bijections you have? So tell me. The bijection, that will be 0, because these are two. Okay, I told you that bijection exists if and only if they have same set, they have the same cardinality. Bijection A to B exists. Bijection exists. I told you this point. Bijection exists if and only if their cardinality is same. If and only if their cardinality is same. Because they have different cardinality, so bijection is not even exist. So number of bijection will be 0. Number of bijection will be 0. Now let's assume you have 3 here, 3 here. Now how many bijections you have? How many bijections you have? What is the number of bijections? So number of bijections from A to B. From A to B. How many bijections you have from A to B? So remember, these are the bijections. If you notice, what you do, fix A. See, this A you fix. This A you fix. A, B, C, this you fix. This B, 1, 2, 3. So this bijection is created. I can create this bijection, 1-to-1 correspondence. I can create this bijection. Fix A. Don't change A. Don't change A. Now you can rotate this in how many ways? This how many ways you can rotate? 3 factorial ways. You can rotate in 3 factorial ways. This is another bijection. Fix A. Don't change A. Don't change A. Don't change A. Don't change A. This is another bijection. Don't change A. Fix A. So just fix A. Then what you do? Fix A. This is another bijection. Similarly, fix A. Don't change A, but you can rotate B. So this B you can rotate. 3, 1, 2. This is another bijection. And finally, this is another bijection. A, B, C. Fix this A, and now 3, 2, 1. This is another bijection. Can I create something else? Tell me, please tell me. Can I create another bijection? Like, can I create this bijection? Anything else can I create? Only 6 bijection I can create. Yes or no? This bijection, can I, like, for example, can I say this bijection? Did I cover this bijection? Like A, B, C. Did I cover this bijection? Just tell me this point. A, B, C, 1, 2, 3. This bijection did I cover? Did I cover this bijection? Please tell me. These two are same. This and this, they are actually same. The third one, they are actually same. this one and this one, they are actually same. So you can notice, yes, this is also covered. Remember, this bijection is same as this bijection. Both are actually same. They are actually same. There is no difference. They are actually same. So only how many bijections you have? So finally, number of bijections. This is the idea. Number of bijections. Okay. From A to B, where cardinality of A, cardinality of B is equal to n. So how many bijections will be there from set A to set B? Number of bijection. Very simple. Fix A. This A you don't change. Don't change A, but permutation of B you can do. What you can do? You can just do like this. Now what you do? You do permutations of B. So here you can put any permutation of B. Any permutation of B you can put. Okay. Fix this. This is fixed. Fix this. Okay. This is fixed. So this order is fixed. This order is fixed. Now what I can do? Now I can put permutations of B here, and okay, these are, so finally I will get bijections. So how many bijections are possible? Number of bijections, what that will be? Number of bijections, that will be n factorial. These many bijections will be there. Very simple. Okay. So finally here, remember, in this case, now you can notice that 3 factorial bijections are possible because vertices of G, there are 3 vertices here, there are 3 vertices here. So between these vertices and these vertices, there are 3 factorial. There are 6 bijections possible, but none of them will preserve edges. None of them will preserve edges. Is it clear to everyone? Please tell me. Okay. So remember, finally, this is the conclusion. Please understand, this is the conclusion of this definition. We will not apply this definition, let me tell you. This definition, can you notice, it will take a lot of time if you apply this definition to check isomorphic. So this is the conclusion of definition. So the definition of isomorphism, and this is the conclusion. What is the definition of isomorphism? Very simple, that you have a graph G in which you have V1 comma E1. This is the graph G, and you have a graph H V2 comma E2. Then G is isomorphic to H if and only if there exists a bijection between V1, okay, between V1 to V2, there exists a bijection from V1 to V2 such that there exists a bijection F. There exists a bijection F from V1 to V2 such that, okay, what? So I can say, so there exists a bijection from V1 to V2. There exists a bijection F such that if this edge, okay, if this edge belongs to E1, if and only if this FA comma FB, means their corresponding vertices. If these two have edge, then their corresponding vertices should have edge. If these two don't have edge, their corresponding vertices should not have edge. Is this clear? And this should happen for all. This should happen for all. This should happen for all A comma B. This should happen. So this should happen for all A comma B, that if they have edge, then their corresponding, then their images also should have edge. If they don't have edge, then their images also should not have edge. So they have edge if and only if they have edge. This is the definition of isomorphism. But this isomorphism, if you apply, for example, let's assume I give you a graph. This is my question. Let's assume you have a graph G, 10 vertices. Okay, you have a graph G with 10 vertices. You have a graph H with 10 vertices. How much time it will take to prove? Okay, if you apply definition to check isomorphism, if you apply definition, then how much time it will take to check isomorphism? If you apply definition, then how much time it will take? Then you have to check 10 factorial bijections you have to check. First of all, 10 factorial bijections need to check. We have to check 10 factorial bijections. These many bijections we will have to check if you have 10 vertices. these many bijections, and this is a very huge value. This value is very big. Okay, so that is the reason we will never apply the definition of isomorphism. The definition of isomorphism we will never apply, never. This definition I told you because in the NET exam, NET, in the NET exam there is a question in which they are asking directly, they are asking definition. There are 4 options, and in those 4 options they are asking the definition of isomorphism. So in the GATE exam also they can do this, because in the GATE examiner knows, the GATE people know that students can find isomorphic. Like if I give you 2 graphs, you can find whether they are isomorphic or not. Many people can do that, but many people don't understand the definition of isomorphism. So in the GATE exam they can give you 4 options, and one of them will be the definition of isomorphism. Other things will not be the definition. Like they can change. For example, they can change something. Okay, in one option they will give you this definition. In another option they will create for all. Okay, in another option they will remove this if and only if, and they will create if. See, in another option they will do this. So basically this type of thing they can do. They can do whatever they want. Okay, so these are the ideas. Anyway, so remember, we will never apply the definition of isomorphism to check whether the graph are isomorphic or not. So what we are going to do, let me tell you few things. So never apply isomorphism definition. Never apply isomorphism definition to check isomorphism, to check if 2 graphs are isomorphic. Okay, to check if 2 graphs are isomorphic. Never apply this definition. So now what we are going to do, actually proving that 2 graphs are isomorphic is very hard. Let me tell you. First of all, let me tell you that if you want to prove, okay, proving that 2 graphs are isomorphic is very hard. Proving graph isomorphism, if you want to prove that 2 graphs are isomorphic, then this problem if you notice, this problem is a very hard problem. This problem is very hard. This problem is known as NP. There is a word for it, that is NP intermediate problem. This is a NP intermediate problem. What it means? NP intermediate problems are those problems which have exponential solution, which have exponential time complexity. So the time complexity is actually exponential for the graph isomorphism. So if you want to prove that 2 graphs are isomorphism, 2 graphs are isomorphic, if you want to prove this, then this problem is very hard. Not simple hard. This is extremely hard. This is NP intermediate, means this has exponential time complexity. But if you want to show that graphs are not isomorphic, showing not isomorphic is easy. Showing not isomorphic is actually easy. Not isomorphic can be done very easily. That 2 graphs are not isomorphic, okay, can be done using something called graph invariants. Using graph invariants, there is something called graph invariants. What are graph invariants? These graph invariants, these are basically the properties. These graph invariants are basically the properties of graph which isomorphic graphs should have. See, remember, these are the graph invariants. So showing that 2 graphs are not isomorphic, that can be done using graph invariants. These graph invariants are properties which isomorphic graphs should have, like properties which should be same in isomorphic graphs. In isomorphic graphs, these properties must be same. Are you getting what I'm saying? Can anyone tell me which properties must be same in 2 isomorphic graph? Graph invariants. Which properties? Graph invariants. Remember, these graph invariants, these are the properties. These are the properties which should be same, which should be exactly same in isomorphic graph. If I give you two isomorphic graph, then what should be same? Number of vertices must be same, yes or no? So the order of graph must be same. Number of vertices must be same. Number of edges must be same. Okay, so means number of vertices must be same. Number of edges must be same. What else? Degree sequence must be same. Degree sequence must be same. And what else? For example, I can say maximum degree must be same. Minimum degree must be same. Okay, maximum degree, minimum degree, they must be same. What else? Number of three length cycles must be same. Number of three length cycles must be same. Number of k length cycle must be same, like 4 length, 5 length. Number of k length cycles must be same. Yes or no? So these properties, if you notice, these are the graph invariants. Means these are the properties which should be same for isomorphic graph. If you have two isomorphic graph, then these properties must be same for two isomorphic graphs. Maximum degree, minimum degree, okay, order of a graph, size of a graph, degree sequence, all these things. Number of cycles. What else? Diameter. What else? Diameter. What else? Connected. What else? Connectedness. Means either they both must be connected or they both must be disconnected. So connectedness. So these concepts, all these concepts, they are basically graph invariants. Is this clear? Is this clear to everyone? One more thing. If all these things are same for two graphs, can I say they are isomorphic? If all these things are same for two graphs, can I say they are isomorphic? No, you cannot say. Remember. If any of these property is different for two graphs, then you can say they are not isomorphic. But if all these properties are same for two graphs, it does not mean that they are isomorphic. Okay, so this is the point. This is the note that, okay, if some graph invariant, there is, like, if at least one graph invariant is different, at least one graph invariant is not the same for two graph, then what can I say? Is not same for two graph. If some graph invariant, these graph invariants, these are the graph invariants, these are the properties. Remember, these are the properties which should be same for isomorphic graph. If some graph invariant is not same for two graph, then they are not isomorphic. Then they are not isomorphic. But remember, if all properties are same, if these, okay, these previous, if previous all graph invariants are same, if previous all graph invariants, remember, all graph invariants are same for two graph, then it does not mean they are isomorphic. Then it does not imply, then it does not mean, remember, it does not mean they are isomorphic. Okay, is it clear to everyone? So these properties are necessary but not sufficient. These properties, all these properties on your screen, all these properties are necessary, but they are not sufficient. These properties, these graph invariants, these are necessary but not sufficient. They must be same for isomorphism, but they are not sufficient. Again, I am telling you, graph isomorphism is a NP hard problem, like NP intermediate problem. Graph isomorphism is very hard problem. Okay, so these are one way. If these are one way, so this is what I'm saying. If some graph invariant is not satisfied, then not isomorphic. But if all graph invariant are satisfied, it does not mean they are isomorphic. It does not mean they are isomorphic. So all these properties, these are necessary but not sufficient. So please understand this. So we have seen the definition of isomorphism. This is the definition of isomorphism. And then we have seen, tell me, okay, let's check. Are these two graphs isomorphic? Tell me. Are these two graphs isomorphic? Don't apply the definition of isomorphism. Just tell me, are these two graphs isomorphic? Yes, these two graphs are isomorphic. What we have to do? Basically, you pick this V3 and you pull this away. What you do? What you do? These are isomorphic because you take this V3, you take this V3 and you untwist this. You take this V3. Basically, this is twisted. I can say this is G, this is twisted G. Actually, they are same because what you can do, you can this V3 you can pick and you can pull it here. Okay, you can untwist. You can untwist. Are these two same? These two graph? Yes, they are also isomorphic. This is also K4. This is also K4. Both of them are K4. This is also complete graph on 4 vertices. This is also complete graph on 4 vertices. Here also every 2 vertices are adjacent. Here also every 2 vertices are adjacent. So because they are K4, K4, so yes, they are isomorphic. What about these graphs? What about these? These two graphs. These two graphs are not isomorphic. Why? These two graphs are not isomorphic. See the maximum degree here. Here the maximum degree is 4. And here the maximum degree is what? Here the maximum degree is 3. If you notice, the maximum degree you can check. Or here you have a pendant vertex. Here you have a pendant vertex. Here there is no pendant vertex. Here we have a degree 1 vertex. Here we don't have a degree 1 vertex. Yes or no? In this H, maximum degree is 4. Okay. Similarly, in this H, if you notice in this H, the degree sequence will be what? The degree sequence is 4. This has degree 4. Then you have a degree 3. Then you have a degree 2. Then you have a degree 2. Then you have degree 1. And what is the degree sequence of G? Degree sequence of G, that is 3, 3, 2, 2, 2. So of course, degree sequence is different. So you can use these things. Because degree sequence is different, so these are not isomorphic. What about these two? Graph G, H on your screen here. What can you say? Are they isomorphic? Why they are not isomorphic? They are not isomorphic. What is the reason? What is the reason? See, maximum degree is same. If you notice, both of these graphs have the same maximum degree is same. Actually, the degree sequence is also same. Degree sequence is also same. Number of vertices is also same. Number of edges is also same. Degree sequence is also same. So what is different? So what is different? 4 length cycles. Let's find out how many 4 length cycles we have here. In this G, how many number of 4 length cycles? What is that? What will be the number of 4 length cycles? So here number of 4 length cycles, if you notice, this is a 4 length cycle 1. This is another 4 length cycle 2. Do we have another 4 length cycles? Like, is there any other 4 length cycle? In this G, we have only 2 4 length cycles. See, this is a 4 length cycle. This is a 4 length cycle. If you notice, there is no other 4 length cycle. These are actually not 4 vertices. These are not 4 vertices. So you should have 4 vertices. Can you create any other 4th length cycle? So in H, how many 4 length cycles you have? How many 4 length cycles? How many 4 length cycles you have? So number of 4 length cycles, that will be, this is a 4 length cycle. This is a 4 length cycle. This is a 4 length cycle. Basically, that is greater than equal to 2. I can say that is 3. Okay, so the number of 4 length cycles, so they are not isomorphic because the number of 4 length cycles is different. You can notice here, number of vertices same, number of edges same, degree sequence same, diameter same, maximum degree same, minimum degree same. But okay, this number of 4 length cycles, that is different. So I can say these are not isomorphic. Is it clear to everyone? Please tell me. So remember, let me just tell you. Now you can notice, what is a graph invariant? The definition of graph invariant. Graph invariant means it does not vary. Invariant means it does not change for isomorphic graphs. If you have 2 isomorphic graphs, then it does not vary. It does not change. Graph invariant is a property of graph that is preserved by isomorphism. If 2 graphs are isomorphic, then they must have same invariants. Okay, this G1 has some invariant property, then G2 also should have same invariant property. Common examples of invariant like number of edges, number of vertices, degree of a vertex, and there are many others. Like these are the invariants. Isomorphic invariant, what it means? These are the properties which should be same for isomorphic graphs, like number of vertices, number of edges. Okay, for example, maximum degree, minimum degree has a vertex of degree k, has m vertices of degree k, has a circuit of length, cycle of length k. Okay, has a simple circuit. Simple circuit means cycle. Actually, some people simple circuit, that simply means cycle. Simple circuit, this is the name for cycle. So has cycle of length k, has m cycles of length k, is connected Euler, Hamiltonian. These things we will study. There are many others like coloring number. Okay, we will study in future. We will study in future coloring number, omega number, independent number. Okay, there are many other concepts. These concepts we will study in the futures. In future we will study these concepts. But the point is that these concepts are also graph invariant. They must be same for two isomorphic graphs. Are these two graphs isomorphic? This is not a vertex. This is not a vertex. Remember, this is not a vertex. So number of vertices is actually same. So why they are not isomorphic? They are actually not isomorphic. What is the reason they are not isomorphic? Can anyone tell me? 4-length cycle. Okay. So here you have a 4-length cycle. Here we have a 4-length cycle. Do we have 4-length cycle here? Can you create a 4-length cycle here? Like, can I create a 4-length cycle here? Can I create 4-length cycle? Yes, this is a 4-length cycle, right? You can go from here to here. You can go from here to here, here to here, here to here. So this is a 4-length cycle. What about 5-length cycle? Okay, so 4-length cycle is not a problem. 4-length cycle is not a problem. What about 5-length cycle? Here we have a 5-length cycle. Okay, like what you can do, you can create a 5-length cycle like this. These vertices, if you take, then you will get a 5-length cycle. Okay, here can we create a 5-length cycle? Tell me, in this graph, do we have a 5-length cycle? 5-length cycle do we have? In this graph, can you create a 5-length cycle? I think in this graph, there is no 5-length cycle, right? In this graph, if you check, please check this. There is no 5-length cycle in this graph. And there is 5-length cycle. There exists 5-length cycle. You can also check maybe like number of vertices is same, number of edges is same, degree sequence, if you check, that is also same. Degree sequence is also same, because here there is no 5-length cycle and here you have a 5-length cycle. So these are not isomorphic. Okay, next, what about these two? Are they isomorphic or not? These two graphs, are they isomorphic? These are actually not isomorphic. And what is the reason? This is degree 4. This is degree 4. Okay, so the degree sequence, I think the degree sequence will work here. For this question, the degree sequence will actually work. This is the degree sequence here. And this is the degree sequence here. So there is no vertex of 3 degree here. There is no vertex of degree 3 in this graph. So the degree sequence will actually work. Okay, so they are different because their degree sequence is different.